This will be the last video on our rotational motion, momentum, and energy set of videos. And we had just been talking about rolling. And rolling is when you have both translational motion, the object is moving from one place to another, but at the same time it's rotating. And we had worked out a formula for the kinetic energy in that case. So it's like our old 1/2 mv squared, except now we have an additional piece that also takes into account the fact that it's rolling adds a little bit more energy to it. Okay, so I want to use this in an example, and in particular, one place that this will affect things is in our old conservation of mechanical energy problems. If we now have objects that are rolling, things will be slightly different. So let's say we have a ball, and here's its stats, and it is let go at the top of an incline of 25 degrees, and it rolls downward. Okay, so how fast is it going when it gets down to the bottom? Or at least, maybe not the bottom, but when it's gone down 1 meter. Now, what I'd really like to do is compare this to how we have done these problems in the past, where we didn't have an object rolling, but instead we would just have an object that was just sliding down, and we assumed there was no friction, or that would have complicated things. So we had a frictionless surface. Okay. Now, the way we did this before is, well, first of all, so rolling 1 meter. So there's a little bit of details here. So to go 1 meter, right here, that's a vertical drop. How much of a vertical drop is it to go down 1 meter? Since this angle is 25 degrees, this would be 1 meter. This change in y would be 1 meter times sine of 25 degrees, which is 0.423 meters. And actually, because we're starting at the top and going down, this is actually a negative, right? The change in y is negative. We drop 4.23 meters going from here to here. And so, okay, so that little bit we had to figure out ahead of time. But the main approach that we did here is we used conservation of mechanical energy, because we would think of the block and the Earth as a system, and it was isolated, at least energy-wise, because yeah, there's normal force from the surface that you're on, but remember, normal force never does any work, so it never adds or subtracts energy. So the block and the Earth and the gravity force between them, that's an isolated system, and gravity is a conservative force, and so we had conservation of mechanical energy. So we could do Ki plus Ui equals Kf plus Uf. Now at the top, we had no kinetic energy because it hadn't started moving yet, but then it starts moving, and then by the time it gets to the bottom, it'll have no potential energy. Because let's say that, so I guess what I want to do is I want to put a y-axis on here and say that the bottom is 0, and then the top would be 0.423 meters. Yeah, let's do it that way. Okay. All right, so at the beginning we have potential energy because we have an altitude, right? So it's mgyi. And then at the end we had 1/2 mv squared, vf squared. And so to figure out how fast this thing is moving when it gets that far down, we're ready to go. We can solve for vf. We would cancel the m's, so we would have 2gyi equals vf squared. So I guess vf would be the square root of 2gyi. The initial y being this 0.423 meters that we got from our little trig triangle thing. All right, and when you plug that all in, you get 2.88 meters per second. Okay, so that was the answer, and those were the kinds of problems we were doing back in those previous, like chapter 6, conservation of mechanical energy. Okay, when the object is rolling, though, we're going to approach it the same way, And we're going to use conservation of mechanical energy, but we won't get the same answer because the kinetic energy is a little different when you're rolling. And in fact, I don't know, like you could think to yourself based on what we've already talked about, is the final answer going to be bigger or smaller? Okay, so I think it's going to be smaller, right? Because more energy is the energy that it's going to pick up as it rolls down. Let me be really correct here. It has the energy, it has potential, but it's going to pick it up as kinetic, right? The potential is going to turn into kinetic. But the thing is now some of that kinetic just has to go into the rotating part of the rolling. And so that'll leave a little bit less energy that can just go into the overall movement of the ball. And that's what we're asking for, right? Like how fast is it going? When we say that, we mean like how fast is the ball overall, its center of mass, how fast is that going? So it's not going to have as much energy left over for that, and we'll see that. So let's do it. Same approach. We're going to do Ki plus Ui equals Kf plus Uf, and 0 to begin with, 0 potential to end with. This will be mgyi. But then the k here, which is not 0 now, is going to be 1/2 m plus, and now here's where we have to add in this extra term, I over r squared. And then Vf squared. This is V center of mass, but I'll drop the Cm. We'll understand that that's what we mean there. All right. So, slightly different algebra. The 2 comes over, 2mgyi. Actually, notice the m does not cancel. Well, I shouldn't say that. Actually, it does. Let me do this a better way. Let's put in the I. So we're talking about a sphere here. And so I didn't say it, but let's assume it was a solid ball. Let's say it's a solid ball. So the I then is, we look it up on our moment of inertia table, 2/5 mr squared. So I is 2/5 mr squared. So that actually goes in here. And you see that actually the r squareds will cancel. So here, let's write this out. mgyi equals 1/2, and then we'll have m plus, and the r squareds cancel, and we'll have 2/5 m. And so actually, so like 1m plus 2/5 m, that's actually 7/5 m right there in parentheses. So we actually have 7/10 m Vf squared equals mgyi. So whereas over here we had 1/2 mv squared equals mgyi, now we have 7/10 m Vf squared equals mgyi. So yes, the m's do cancel now. Once I put in the I can see that the m's canceled. So now it's going to be 10/7 gyi equals Vf squared, or Vf equals square root of 10/7 gyi. 10/7 instead of 2. That's a smaller number there, right? That's 1 point, I don't know, 4 or something like that. And what's the final answer? 2.43 meters per second. So as expected, it's not going as fast when it gets to the bottom. Again, the reason, to put succinctly, is some of the energy that it had, some of that potential energy, had to be converted to the rotational part of the kinetic energy, leaving less for its overall speed, its overall kinetic energy. And so literally, if we had these two situations, a ball on an incline and then a block on a frictionless incline, and we both let them go, the block would actually win the race. The block would get to the finish line before the ball did. Okay. As something for you to think about, and when we meet, we'll answer this question then. So a block would win. A block that was free to slide down an incline would beat a rolling object. But what about two rolling objects? So suppose we have a ball and we have a cylinder. So a sphere and a cylinder, let's say they weigh the same and they have the same radius, and we let them both go, which one would get to the bottom faster? Which one would win? So think about that. You could even see if you could try to do the work and figure it out officially. But we'll do that in class. And what I just want you to think about is place your bet. Which one do you think would get down to the bottom first, a sphere or a cylinder? Do you think they'd be the same? Or do you think the sphere would get there first or the cylinder would get there first? Okay.